second अपना ये Good afternoon, all of you. In this particular session of thermodynamics chemistry, we are going to discuss about free energy and spontaneity of a process. So, the first thing is that free energy, actually we don't measure the absolute value of free energy. Okay, so free energy we measure the change, we don't measure the absolute value. So the change in free energy is change in enthalpy minus T into delta S. So this is the formula which enables us to find out the change in free energy. Okay, so delta G is equal to delta H minus T delta S. So this is the formula to find the change in free energy. Now in this formula, if delta G is less than 0, okay, if delta G is less than 0, then the process is called spontaneous. And obviously spontaneous means that T will be greater than delta H by delta S. Okay, so if delta G is less than 0, we consider it to be spontaneous. And if you put this thing less than 0, then T is coming greater than delta H by delta S. Okay, now what happens is that at standard state, standard state means what? 298 Kelvin and 1 bar pressure. So at standard state, the free energy change of a reversible reaction, reversible I'm talking in the sense, in chemical equilibrium and in chemical equilibrium, so the reaction can go forward and backward both. So reversible in that sense. So the equilibrium constant of the reaction is K. So change in Gibbs energy at standard state means 298 Kelvin and 1 bar pressure, is minus 2.303 RT into log K to the base 10. So this is the change in Gibbs energy at standard state. Now suppose there is a reaction where A changes to B plus C, where there is a reaction where A changes to B plus C. So initially there is 1 mole of A 0 mole of B and 0 mole of C, and alpha is the degree of dissociation. Okay, so that means that at equilibrium this will become 1 minus alpha, this will become alpha, this will become alpha. So alpha is the degree of dissociation, 1 will become 1 minus alpha, 0 will be alpha, 0 will be alpha. So total moles at equilibrium will be 1 minus alpha plus alpha plus alpha, that is equal to 1 plus alpha. So Kp, suppose the pressure of this reaction mixture is P, like the overall pressure of the reaction mixture is P. So Kp will be alpha by 1 plus alpha into P, again alpha by 1 plus alpha into P, whole thing divided by 1 minus alpha by 1 plus alpha into P. So after calculation it is coming P alpha square So after simplification, it's coming P alpha square by 1 minus alpha square. So once we know the value of Kp, so we can go back to this equation and we can write delta G naught is minus 2.303 RT log Kp to the base 10. So this is broadly speaking how you can approach any question of chemical equilibrium. Okay, so that gives the free energy at standard state. This is the general equation, and in case of gaseous reactants and products, so you can substitute K by Kp and you can find Kp like this. And obviously this is what we do in chemical equilibrium. Okay, now one important thing is that this is the formula for Gibbs energy change. So in standard state the formula will be like this, and in equilibrium the Gibbs energy change will be 0. So equating this to 0, we will get T equal to delta H naught by delta S naught. So if the reaction is in equilibrium, okay, then the corresponding temperature we can get it like this, delta H naught by, so this is for equilibrium. So the corresponding temperature at which equilibrium is coming is given by this. Okay, now as you can see that for finding Gibbs energy change, you have to depend on entropy change. So entropy change is an important term for calculating Gibbs energy change. So if it is a reaction, then entropy change of the reaction is entropy of the products minus entropy of the reactants. So like I said, for Gibbs energy change you have to depend on entropy change, and if it is a reaction, entropy change for any reaction is given by entropy of products minus entropy of reactants. Okay, now uh, there is another alternative way to write Gibbs energy change without, uh, or rather, there is a way to relate this entropy change that is called Gibbs-Helmholtz equation. So, according to according to Gibbs-Helmholtz equation, change in Gibbs energy at standard state is change in enthalpy at standard state plus P into d delta G naught by dt at constant pressure. So this reaction we can also write it like this. So we can write it like this. Meanwhile, we already know that delta G at standard state is delta H at standard state minus T into delta S at standard state. So what we can now do is that we can combine these two. Okay, we can combine these two. And after combining these two, we will get this as the result. Okay, so we can, from here we will get delta G naught minus delta H naught by T is equal to this, and delta G naught is delta H naught minus T delta S. Now if you combine these two, then you will get minus delta S naught equal to this. So by combining these two. So that means what? What are the equations we have seen till now? One is that Gibbs energy change, delta H minus T delta S. Secondly, at standard state, delta G naught is related to equilibrium constant, and you can use a reaction of gaseous reactant and product to find Kp. Then delta G naught will be this. For a reaction which can go both ways, forward, backward, at equilibrium delta G naught is 0, so this is the equilibrium temperature. In all examples of delta G, you have to find delta S. If it is a reaction, this is the method to find delta S. There is another way to relate entropy change with Gibbs energy change. This equation is called Helmholtz-Gibbs equation. So it can be rewritten like this. Meanwhile, delta G naught is delta H naught minus T delta S. If you combine these two, minus delta S naught will be this. So this is another alternative way to relate change in entropy with change in Gibbs energy. Okay, now let's be very clear about one thing. All the terms in this chapter which are exclusive to this chapter, which we never heard before this chapter, all of them have got some physical significance. Like in this chapter, thermodynamics, whatever new terms we have encountered, like the terms which we never saw before this chapter, they all have some physical significance. So the first new term we saw in this chapter was internal energy. So internal energy literally means total energy of the system. Like it can be electrical, mechanical, chemical, whatever. The second new term we encountered, like I'm talking about the absolutely new terms, like not the ones which are carry forward from states of matter like pressure, volume, not like that. The second new term we saw was enthalpy. So enthalpy means heat content of the reaction. Okay, then we saw entropy in the last session. Entropy is the randomness of the system. Like if the system is more random, entropy will be more. If it is less random, entropy will be less. Now today we have seen this new term Gibbs energy. So the Gibbs energy, what is the physical significance of Gibbs energy? Actually, whenever a process is being undertaken from state 1 to state 2, then whatever maximum work you can extract from the system, the maximum work that you can extract from the system, that is called change in Gibbs energy. That is the literal or the physical significance of Gibbs energy. So if you are talking about an electrochemical cell, then this will be the formula change in Gibbs energy is minus n into F into E naught cell. This is the formula. E naught cell is the EMF of that cell at standard state. This is change in Gibbs energy at standard state. N is number of electrons exchanged and F is called Faraday, which is equal to 96,500 coulombs. And now if you combine these two, so delta S naught is N into F into d E naught cell by dt at constant pressure. So if you combine this one and this one, delta S naught is NF into d E naught cell by dt at constant pressure. Now this dE naught cell by dt at constant pressure, this is basically what? This is variation of EMF with temperature, right? Variation of EMF with temperature, and it is called temperature coefficient of EMF of a cell. So this is another important new term, dE naught cell by dt at constant pressure. This is called temperature coefficient of EMF of a cell. Okay, another important relation of Gibbs energy change. Delta G is delta G naught plus 2.303 RT into log Kp. Right. This is the relation between Gibbs energy change and Gibbs energy change at standard state. This reaction will be very, very useful later on when we do electrochemistry. It will be very useful. This is the basic starting point of electrochemical cell reaction. So that we will discuss when we do electrochemistry. Now, what we are discussing today is Gibbs energy change and spontaneity. So the rule is very simple, that if the Gibbs energy change is negative, it will be spontaneous. If the Gibbs energy change is 0, it will be equilibrium. And if it is positive, then of course nothing will happen. I mean, it will not be spontaneous, as in non-spontaneous, as in you will have to trigger the reaction. You will have to force some changes in the reaction to make the reaction happen. On its own, it will not happen. So delta G less than 0 is spontaneous, delta G equal to 0 we have already seen is equilibrium. and positive means that it is not spontaneous. You will have to trigger the reaction. Now, what happens is that it's kind of difficult to talk about this delta G for specific reactions, but unless some temperature or pressure or catalyst is required, you can assume that the reaction is spontaneous. Like this very famous reaction NH3 plus HCl is NH4Cl. So this is a spontaneous reaction. It doesn't require temperature, it doesn't require pressure, it doesn't require catalyst. And the other thing, of course, is that the full equation of delta G, it involves knowledge of enthalpy and entropy. So in this case, of course, two gases are giving us solid, so entropy is going down, but enthalpy is negative due to exothermic. So like I said, if a reaction has no overbearing condition like temperature, pressure or catalyst, then it's not too difficult to comment whether delta G will be negative, delta H will be negative, delta S. Obviously here delta S will be negative because you are getting a solid out of two gases. Delta H is negative, it's exothermic, and there's nothing to trigger the reaction, it's happening on its own, so it is spontaneous. So this is just one example. My point is, when there is no cause to trigger the reaction, usually it is spontaneous. Okay. Now, coming back to the equation, delta G naught is delta H naught minus T delta S. So minus 2.303 RT log K. Delta H naught minus T delta S naught. So log K is minus delta H naught by 2.303 RT plus delta S naught by 2.303 R. So there are a few sums which are involving this relation. So you can see that there is a log K on the left, it is having inverse proportionality to temperature. So this is there are a few sums which are based on this equation. So you can just keep this in mind for doing a few select questions, right? Okay, so with that we come to an end of the theory of today's session, that is Gibbs energy change and spontaneity, and as usual I'll give you the 5 homework questions. So CaCO3 becomes CO plus CO2. At 1000 degrees Celsius. So delta G naught is minus 27,000 joules per mole. Pressure of carbon dioxide, these two are solid, is 0.00333 atm. So the question is, what is delta G? And options are minus 60.5 kilojoule per mole. Second option is minus 87.5 kilojoule per mole. Third option is minus 33.5 kilojoule per mole, and last option is 33.5 kilojoule per mole. So this is the first homework question. Calcium carbonate gives CO plus CO2 at 1000 degrees Celsius. Delta G naught is minus 27,000 joule per mole. Pressure of CO2 is 0.0033 atm. What is delta G for this reaction? And these are the options: minus 60.5 kilojoule per mole, minus 87.5 kilojoule per mole, minus 33.5 kilojoule per mole, and 33.5 kilojoule per mole. Question number 2. So A is changing to B. So the enthalpy change standard state 298 is minus 54.07 kilojoule per mole. So, and entropy change is 10 joule per mole Kelvin. Capital R, you know the units, usual value 8.314, and one hint is given that the product 2.303 into 8.314 into 298, this product you have to take it as 5705. So enthalpy change at 298 at standard state, that is minus 54.07 kilojoule per mole. Entropy change at 298 is 10 joule per mole Kelvin. Capital R usual value, product of 2.303, 8.314 into 298 is 5705, it is given. So actually this is a slightly old J advanced question, 2007. So the question is actually that for this reaction you have to find log K to the base 10, and the options are 5, 10, 95 and 100. Okay, so these are the options. This is question number 2 of today's homework. Then we move on to question number 3. So NiO is converting to Ni plus half O2. So delta G 1729 joule per mole. Temperature is 300 Kelvin. Log 5 is 0.6990. So what is the pressure? What is the pressure of this oxygen? So options are 0.301, 0.699, 0.5 and 0.25. These are the options. Okay, and the last homework question, that is question number 4. So change in enthalpy of vapor is 30 kilojoule per mole. Change in entropy is 75 joule per mole Kelvin. So what will be the temperature at 1 atmosphere? Options are 400 Kelvin, 350 Kelvin, 298 Kelvin and 250 Kelvin. These are the four options. By the way, this is also a very old J advanced question 2004. So the change in enthalpy of the vapor is 30 kilojoule per mole. Change in entropy is 75 joule per mole Kelvin. What is the temperature at 1 atm? Options are 400 Kelvin, 350 Kelvin, 298 Kelvin and 250 Kelvin. So that completes our session of today. That is Gibbs energy, spontaneity and the 4 homework questions of this particular topic. That's it for this session. I'll end now. Okay, I'm ending this session.